In the application of differential equations, we often deal with time-dependent processes where information is available at specific instances, usually the initial instant, time is equal to 0. For example, solve this equation, ds by dt. As we've discussed in class, ds by dt means the change in position with respect to time. So this is our velocity function. The change in position with respect to time is equal to 2t, with the initial condition that our position at time 0 is equal to 3. So our job is to find, doesn't say, our job is to find our position function. Oh, solve this. Okay, so when it says solve this, it's that we're looking for the function s at t. What is that function? So there's our goal, and this is what we know. I'm going to write it over here. I've got the change in position with respect to time is equal to 2t. I'm going to take and multiply both sides of the equation by dt. Then I have ds is equal to 2t dt. What does this mean? The derivative of s. So if I integrate both sides, doing the same thing to both sides, the equal sign, then I'm taking the antiderivative of the derivative of s. I'm going to be left with s. Inverse operations of each other. The antiderivative of 2t is 2 times t squared divided by 2. Just gives us t squared plus a constant. So our function s at t, position at time t, is equal to 2t squared plus c. Go back to our initial conditions and solve for c. That is, our function s at time is equal to 0 is equal to 3. What's s at 0? It would be 0 squared plus c is equal to 3, which tells us c is equal to 3. So what is s at t? Just fill in the blanks. It's equal to t squared plus 3. So when we know the derivative of our function, we work backwards to find the integral, the antiderivative of our function. So the antiderivative of 2t is t squared plus a constant. Do we know that's true? Well, if I differentiated this, would I get 2t plus 0? Yes, I would. So then I use my initial conditions to solve for the constant. Second example, find the curve that passes through the point -1, 0 and satisfies this differential equation. The derivative of y with respect to x is 6x squared plus 6x. So that's telling us that dy is equal to 6x squared plus 6x dx. And then if I do the same thing to both sides of the equal sign, I take the antiderivative, then the antiderivative of the derivative of y is y, which would equal the antiderivative of this side, 6x cubed over 3, plus 6x squared over 2, plus a constant. Let's just simplify that. Y is equal to 2x cubed plus 3x squared plus c. Let's check that the derivative of this gives us this equation. If I took the derivative, I'd get 6x squared, check, plus 6x, plus the derivative of a constant, 0. So here's my equation. How do I find out what that constant is? I substitute in the value when x is -1, y is 0. So when x is -1, y is 0. And solve for c. So what does this give me? 0 is equal to negative 2 plus 3 plus c, or moving everything to one side, collecting like terms, c is negative 1. My equation then, y is equal to 2x cubed plus 3x squared minus 1. So here is the curve that passes through this point and satisfies this differential equation. That means that the point negative 1, 0 is on this curve, and the derivative of this curve is this equation.